Imagine you're watching a master mechanic, and they're rebuilding this high-performance engine, but, and here's the crazy part, the engine is still running.
Oh, wow. That sounds, incredibly dangerous.
Right. It's terrifying. You're just standing there and they're like swapping out parts, rerouting fuel lines, tightening belts, and the pistons are firing the entire time. The exhaust is humming.
Just one slipped wrench and...
Exactly. One dropped wrench, one tiny miscalculation, and the whole system just completely seizes up.
Yeah.
And today, we are actually looking at a developer who did exactly this to a software system. They basically ripped out its core safety net, like a piece of code that was specifically designed to prevent crashes because they realized that very safety net was blinding the system to reality.
It is a super high-stakes operation to picture. But, sometimes those mechanisms we build to keep us safe, they end up becoming the exact things that make us totally vulnerable to the real world.
Yeah, the unpredictable chaos. Welcome to the Deep Dive. Our mission today is to explore a highly specific, yet I think universally relevant structural change. We're looking at how to handle things when a system inevitably goes wrong.
Which they always do.
Oh, guaranteed. So we're dissecting this fascinating structural teardown from a developer named Ang. It's based on an excerpt from a blog post titled Notes-on-Haskell-Programming. Specifically Part 212.
Yeah, Part 212.
Yeah, subtitled Moving from ExceptT to Native I/O Exceptions. It was published on August 13th, 2026.
Just the fact that we are on Part 212 really tells you something about the sheer dedication to documenting this engineering journey.
It really does. It's a journey. Now, for you listening, I want to acknowledge something right out of the gate here. You might not write code in Haskell. You might not write code at all.
Right.
But you are absolutely going to want to stick around for this, because how a system handles unexpected, messy, real-world failures, that is a core concept that applies to literally everything.
Oh, absolutely.
Whether it's like a missing file in a database, a disrupted shipment in a supply chain, or a sudden crisis in a corporate management structure. How you architect your response completely changes the survival rate of the system. Okay, let's unpack this.
Yeah, to really appreciate the tension here, I think we have to talk about the environment Ang is working in. Because Haskell is not... It's just not like your everyday programming language.
It's a whole different beast.
Right. If you look at languages like Python or JavaScript, they are highly permissive. They expect things to be messy. But Haskell, it's built on this philosophy of absolute mathematical purity.
Pure logic.
Yes, pure logic. In a pure Haskell function, a specific input will always, without fail, produce a specific output. The code basically exists in a perfectly sealed theoretical vacuum.
But applications can't just live in a vacuum, right? They eventually have to talk to the outside world.
Exactly. They have to read files from a physical hard drive, pull data from the internet.
Wait for a human to smash a keyboard.
Yeah, exactly. And that part of the code is called I/O, or input-output.
And the outside world is anything but pure. Like a hard drive might be corrupted, a server goes down, or, someone literally trips over the power cord to the router.
Precisely. Those physical, totally unpredictable realities are what we call runtime I/O exceptions. And to protect their mathematically pure logic from all this chaos, Haskell developers traditionally use something called a monadic transformer layer.
Which sounds like something out of Transformers.
It does, but in Ang's case, it's a specific tool called ExceptT.
And this is where we run into the massive problem that forced this whole engine rebuild in the first place. Ang realizes that this ExceptT layer, this safety net, has a massive blind spot. It is completely failing to catch these runtime I/O exceptions.
It's just ignoring them.
Right. So to picture this, I like to think of ExceptT as a highly bureaucratic security guard working the front desk of a pristine corporate building.
Okay, I like where this is going. How does this guard operate?
So this guard is incredibly diligent about checking for expected business logic errors. They are checking badges. If your ID is expired, or if you just don't have clearance for the 4th floor, the guard catches it immediately. They log the error perfectly, and they turn you away.
That maps perfectly to application errors. The guard forces the developer to explicitly handle known scenarios, like user not found or invalid password.
Right. The guard is following a strict set of predefined rules. But, and here's the fatal flaw, the guard is so hyper-focused on the badge scanner that they completely ignore the fact that the physical building is catching on fire.
Oh, wow.
The fire is a runtime I/O exception, a file goes missing, or the operating system just flat out denies read permissions. Those are physical level errors. And ExceptT, our very diligent guard, just lets the fire burn because, fire wasn't on the list of expected badge errors.
Right. It literally cannot perceive the fire. What's fascinating here is how this exposes the friction between pure logic and reality. The ExceptT transformer, it forces the developer to acknowledge the errors they know about. But the real world just bypasses the badge scanner entirely.
But hold on, if ExceptT completely misses these physical level errors, if it misses the literal fires, why would a developer ever use it in the first place? I mean, it sounds kind of useless.
Well, it's not useless, but it is highly specialized. Think of it as a tool that is meant strictly for that sealed vacuum we talked about earlier. In the purely logical parts of an app, where there's no physical hardware involved. ExceptT is fantastic.
Oh, okay, so it keeps the pure stuff safe.
Exactly. It ensures you never accidentally ignore a business logic error. But Aang reaches a critical realization here. When your application is heavily reliant on I/O, when it is constantly talking to the messy outside world, maintaining that theoretical purity becomes a dangerous liability.
You just can't afford it anymore.
Right. The application has to abandon this bureaucratic middleman and move towards standard Haskell native I/O exceptions just to survive.
Okay, so if the bureaucratic guard is completely ignoring the fires, how does the system actually recognize the smoke? This is where Aang has to fundamentally rewire the alarm system. And it starts with this very first structural change, elevating something called aperture.
Yeah, and this is the brilliant structural shift. Aang takes the existing known application errors, so the badge errors from your analogy, and decides to elevate them to the status of a native exception. In the code itself, Aang does this by deriving the exception instance for aperture.
So by deriving that instance, like what is mechanically happening under the hood there?
Mechanically, Aang is giving these custom application errors a VIP passport to travel through the language's core emergency response system. Previously, these errors were basically trapped inside the bureaucracy of ExceptT.
Stuck at the front desk.
Exactly. But now, they can be thrown and caught natively in I/O. They are integrated directly into the foundational layer of the language itself.
And Aang doesn't just stop with upgrading the old errors, right? Aang adds entirely new, dedicated I/O-related failures to the codebase.
Right, the real-world stuff.
Yeah. We see the addition of things like read failed, write failed, open failed, and then this catch-all category upon an unexpected error. And Aang sets it up so these are rendered for the user via a display error function. So if a file just can't be read, display error takes that read failed event and spits out a clean message like error.failed to read file, and then followed by the actual file path.
Which bridges a massive gap in the system, because now you have existing errors from the application's domain-like unsupported format sitting right alongside these new raw physical I/O errors, like read failed. They are all grouped under one unified exception type.
But let me pause you on that list, though, because I see read failed and write failed, and those make perfect sense. But then there is unexpected error. So what does this all mean? Like, is adding an unexpected bucket just a lazy way out for a developer who doesn't want to define all the proper errors?
It is really easy to view it that way from the outside. But structurally, it is the exact opposite of laziness. This is about graceful degradation.
Okay, how so?
Well, by elevating aperture to be thrown and caught natively, the application can now catch every single error once, at the very top of the app, and render it cleanly. Unexpected error isn't giving up. It is a critical safety net for the unknown unknowns.
Right. So if we relate this back to, like, organizational management, this is like a CEO finally admitting they cannot possibly predict every single micro-market shift or supply chain hiccup.
Yes.
Instead of writing 100 highly specific contingency plans that might all be wrong anyway, they just build a massive overarching cash reserve.
That is a perfect parallel. If an operating system throws a totally bizarre, highly specific kernel error that Aang could never have anticipated, the application doesn't just crash. It doesn't dump a terrifying page of raw code onto the user's screen.
Right, which we've all seen and panicked over.
Exactly. Instead, it catches that bizarre exception, wraps it securely in that unexpected error bucket, and politely tells the user, error, unexpected, followed by the message. It is about maintaining control even when the system is fundamentally failing.
I love that. Okay, so now that this unified safety net is in place, Aang can start gutting the bureaucracy. We see the actual flow of the program completely change. In the main control flow, a function appropriately called runapp Aang just goes to town.
Yeah, complete overhaul.
The ExceptT unwrapping is completely ripped out, and it's replaced with native try-and-throw IO exception handling.
This is the moment where the code literally physically shrinks.
Yeah.
You can see the bureaucratic layers just being peeled away from the logic.
And we see this super clearly in the main conversion function, which Ang calls pipeline. Ang drops the ExceptT apper IO wrapper from its signature entirely. It just becomes a plain IO.
Just clean IO.
Right. And the part of the code that handles pure either returns, so a function that returns either a success or failure, that's converted into native exceptions using this one tiny phrase, either throw IO pure.
Oh, either throw IO pure. It is an incredibly elegant, dense line of code.
Here's where it gets really interesting. Let's break that down because the mechanism here is so cool. I picture either throw IO pure, kind of like a strict bouncer at an exclusive club.
Okay, a strict bouncer. Walk me through this.
So, imagine you're walking up to the door of this club. The bouncer has a clipboard. If your name is on the guest list, meaning the transaction is pure, it's a success. The bouncer just waves you right in. You say pure, and you go inside.
Right, no hassle.
But if there is an error, any error at all, you're not on the list, the bouncer doesn't try to negotiate, they don't call the manager, they don't fill out a form, they just grab you and immediately hurl you out of the building. That is the throw IO. You are instantly ejected.
That is exactly how the bubbling up mechanism functions here. And the beauty of this refactor is how it completely bypasses the middle layers of the architecture. Because native exceptions automatically bubble up or get hurled out of the building by the bouncer, the code no longer needs that heavy transformer wrapper to carry the error by hand from function to function.
Yeah, the middle managers are just gone.
Yes. Because of this, that single try block up in the run-up function, the top level, it now catches absolutely everything. It catches the explicitly defined standard apper values like read failed, and it catches those totally unknown runtime exceptions stuffed into the unexpected error bucket. Everything just converges at one single manageable checkpoint at the top of the app.
It's a massive structural cleanup. You can almost hear the engine running smoother, which I guess leads us to the final step of the refactoring, because Ang shows how cleaning up this high-level architecture at the top actually cascades all the way down. It simplifies the really granular low-level functions at the bottom.
Yeah, it creates a ripple effect.
The core example Ang gives is a function called parse input.
Right, parse input is where the application actually takes the arguments provided by the user, figures out what file to look at, and then tries to read it. It is the absolute front lines of the I/O operations.
Where the messy real world meets the logic. And Ang just strips it down to the studs. Ang drops the either apper from the return type completely. Monadic throw-where commands are replaced with throw IO to let the bouncer toss them out. And then something called liftIO calls are just completely deleted.
And those liftIO deletions are so crucial to understanding the relief this refactor brings to the system.
Let's talk about liftIO, because earlier we mentioned how Haskell despises the messy outside world. I kind of think of liftIO as a hazmat suit.
A hazmat suit, that's good. Because Haskell doesn't want unpredictable real-world data touching its pure math, developers have to explicitly write a command liftIO to put a hazmat suit on every single file raid, every network request, every keyboard input. And Ang realized the entire application was practically suffocating in these hazmat suits.
It creates an immense amount of visual noise in the code. liftIO was basically the code begging the compiler, like, please take this messy real-world action and lift it up into my pure, protected monadic wrapper.
By switching to native exceptions, the wrapper is just gone. The application finally embraces the fact that it lives in the real world, so the hazmat suits can come off, and the code can just execute the action directly.
Which is so much cleaner. And Ang implements a specific try block just for reading the file using bl.read file, and then maps any failures there to brand new, highly specific exceptions. Things like file not found, not text file, and invalidipif8.
Which are very concrete, real-world problems.
Yeah. But looking at all of this, looking at how parse input is stripped down, I have to challenge the overarching philosophy here, because Ang dropped either apper from the function's type signature.
Yes, the signature was simplified.
But for someone who doesn't read Haskell every day, let's establish what a type signature actually is. It's essentially a warning label printed right at the top of a function.
Like a nutrition label.
Exactly. It tells the developer exactly what inputs are required and what outputs or errors might come out. In the previous setup, any developer looking at the warning label of parse input would see either apperer and instantly know, this function might fail, and it will fail specifically with an apperer.
Right. It was explicit.
But by dropping that from the label, aren't we losing vital information? Doesn't the function become fundamentally less descriptive and maybe even more dangerous for other developers to use?
If we connect this to the bigger picture, you are hitting on one of the oldest, most passionate debates in software engineering: explicit, highly typed errors versus implicit runtime exceptions.
Ah, okay.
You are absolutely right that the new warning label tells you much less about the specific failures, but the trade-off Ang is making here is entirely about reducing cognitive load.
When you say cognitive load, you mean just the mental energy required to read the code.
Exactly. When every single function in a massive application has to explicitly list every single error it might possibly encounter, that warning label becomes longer than the actual instructions. Imagine buying a toaster, and the warning label is like a CVS receipt that lists every possible electrical grid failure in your city.
Oh man, that would be exhausting. You'd never even plug it in.
Exactly. It becomes a chore to read and a total nightmare to maintain. By switching to native I/O exception handling, the type signatures across Ang's entire pipeline are radically simplified. The cognitive load just plummets. Ang makes the actual business logic, the story of what the program is trying to achieve, infinitely more readable.
So it is really a battle of signal versus noise.
Yes.
The explicit bureaucratic error types were creating so much noise that it was becoming impossible to hear the signal of what the code was actually doing.
Precisely. Ang traded microscopic, function-by-function safety for macroscopic clarity and real-world resilience. It is an acknowledgement that in an I/O-heavy application, things are going to fail in completely unpredictable ways. It is ultimately better to have a robust, unified way to catch those failures at the top than to try and micromanage them at every single step of the journey.
It really is a masterclass in pragmatic engineering. If we pull back and look at Ang's whole journey in part 212 of these notes, the evolution is striking. We started with the blind spot of ExceptT, or bureaucratic security guard, that dutifully checked badges but totally failed to catch low-level real-world fires.
Right.
And Ang solved this by moving the engine away from theoretical pure wrappers and switching over to native I/O exceptions.
Which fundamentally unified the error handling of the entire system. Instead of passing errors up by hand through endless layers of middle management, they now just shoot straight up. They bubble up instantly to be caught by a single try block at the highest level of the application.
The CEO's desk.
Exactly.
And the downstream effects of that single architectural decision were incredible. It simplified the warning labels on the functions, it allowed the code to take off those clunky liftIO hazmat suits, and it made the granular low-level functions so much cleaner to read and write.
It's a huge win for readability.
For you listening, I think the takeaway here goes way beyond Haskell and honestly way beyond software engineering. In any complex system, whether it's a sprawling code base, a global manufacturing pipeline, or even a corporate management structure, human beings have this natural tendency to build complex, bureaucratic middlemen to handle things when they go wrong.
We really do. We love building a bureaucracy because it gives us the illusion of control. It feels safe. It makes us feel like we have planned for every single contingency.
But sometimes stripping away those middlemen in favor of native, direct communication leads to a cleaner, faster, and ultimately safer environment. Sometimes you just have to stop micromanaging the errors on the ground floor, accept that the real world is messy, and just build a better, wider safety net at the very top.
It takes immense confidence to strip away the safety wheels of explicit error handling. But the resulting system is undeniably more capable of handling the harsh realities of its environment.
It truly is. But as we wrap up, I want to leave you with a final thought to mull over, one that really applies to any team or organization. We talked deeply about the trade-off Ang made by dropping those explicit errors from the function signatures. Switching to native exceptions undeniably simplified the code by letting errors invisibly bubble up to the top. But how does this fundamentally change the way developers mentally model their applications?
It shifts the entire burden of awareness.
Exactly. Does making the errors invisible on the warning label actually make a system inherently harder to reason about for a brand new developer?
That's the question.
If you're looking at the code for the very first time, and the signature doesn't explicitly warn you about the specific dangers lurking inside that function, are you more likely to get burned? It's this fascinating tension between making the system cleaner to read and making its inherent dangers harder to see. Think about that master mechanic again. They successfully rebuilt the engine while it was running, and they stripped away all the unnecessary bureaucratic parts to make it hum. It runs beautifully now, but if a brand new apprentice walks into that garage tomorrow morning, will they know which wires are live? Thanks for joining us on The Deep Dive.